Today we'll study fuzzy rules and fuzzy reasoning. All of you know about rules and reasonings. Now the outline of this chapter is extension principle, fuzzy relations, fuzzy if-then rules, composition rules of inference, and fuzzy reasoning. So we know the relations in creep sets. Now we'll study this on fuzzy sets. So first we will know what is extension principle. If A is a fuzzy set on universe of discourse X, then A is you can written as mu A of x1, mu A of x2, and mu n of xn for all points x1, x2, xn belongs to the universe of discourse X. The image of A under the function f is a fuzzy set B, then B is equal to mu B of x1 at y1, mu B of x2 at y2, and mu B of xn at yn, where y of I is equal to f of xi and I runs from 1 to n. Now if this function f is a many to one functional mapping, then this mu b of y can be calculated. This is equals to maximum of mu a of x1 x, where x is f inverse of y Now we'll go to fuzzy relations. First we'll study for two-dimensional membership functions. As you are all acquainted with the relations in two-dimensional, so we are finding the all possible ordered pairs to find the relation R. Similarly, a fuzzy relation R in a 2D membership function is given by R is the set of all ordered pairs xy with its membership functions, functional values mu of xy under the relation R, where xy is an ordered pair which is an element of x cross y. So what about x cross y? So x and y are two different universe of discourses and R is defined from x to y. R is a relation from x to y. So we are finding the relation mathematically. It is a set of all order pairs with its membership functional values. For examples, x is close to y. X for x and y are numbers. X depends on y. If x and y are events, x and y look alike. For x and y are two persons or objects. If x is large, then y is small. X is where x is an observed reading and y is the corresponding action. Then these are the examples of fuzzy relations to define the x and y variables. Now to find this membership function of two relations R1 and R2, if R1 is a relation from x to y and R2 is a relation from y to z, where x, y, z are three universe of discourses. Suppose we will find the composition of relations R1 of R2. So first of all we have to find the membership functional value. for R1 over R2. Since we are finding the composition relation, the R1 over R2 is from the universe of discourse X to Z. So how to find it? We'll find it by using maximum composition. It's given here mu of R1 of R2 xz is equal to union of mu R1 xy intersection of mu R2 yz, where y is the universe of discourse lying between x and z. Now if R, S and T are three relations, then R of S of T is R of S of T. These are some formulae regarding to the relations. R of S union T is R of S union R of T. R of S intersection T is subset of R of S intersection R of T. S is subset of P. T implies R of S is subset of R of T. Now max product composition. The mu of R1 of R2 xz same as union of mu R1 xy mu R2 yz. General. Now we'll find some linguistic variables. A numerical variable takes numerical values, that is age is defined as suppose 65. Linguistic variable takes linguistic values, age is old. A linguistic value is a fuzzy set, and all linguistic values form a term set that is denoted by T of, suppose you are finding the age as linguistic value or variable, then T of age may be young, not young, very young, middle age, not middle age, old, not old, very old, more or less old, not very young or not very old. And so a lot of terminologies are coming and you are not finding any concrete answer. A lot of answers are coming if it is defined on age. Now these linguistic values can be given by membership grades or membership functional values. So we will take in x-axis the ages and y-axis in membership grades or membership functional values. Then the first one gives the primary linguistic value and the second one gives the composite linguistic value. But in first one we are considering young or old, but in second case we are considering young but not too young, not young, not old, more or less old, extremely old, and all terminologies you are having. These are some examples are given here. Now we study some operations on linguistic values. Concentration. Number 2 is dilation. Contract intensification. So concatenation of A means you will find A of 2 with power 2 or A of 2. Dilation means A power half. Intensification means int of A is 2 of A square and like this. I'll go to fuzzy reasoning. First we'll go for single rule with single antecedent. So if you're applying a rule on a variable, we'll find some conclusion that's known as antecedent or output or outcome. The rule is if x is a, then y is b. The fact is here x is a, that is given, and conclusion or finding y is b. Now the graphical representation of the same rule is a is given, we are finding y is b. X is a given and we are finding y is b. Graph is given like this. Then we will find some multiple antecedents. If x is a and y is b, then z is c. So two conditions are given. X is a and y is b, then we are finding conclusion z is c. So fact is x is a and y is b. The conclusion is z is c. So these are the graphs given as shown in the figure. So you find the result z. I'll go to multiple rules with multiple antecedents. So if rule 1 is if x is a1, y is b1, then z is c1. Rule 2 is x is a2, y is b2, then z is c2. Now the fact given here out of the two rules, x is a and y is b, then conclusion is z is c. So how graphically you can represent it? These are the graphical representations of multiple antecedent with multiple rules.